This is an example of another way of finding the required medicine a patient can get dependent on their weight. And this is done using proportions rather than unit conversions. So here we have 5 milligrams per medicine for every kilogram of weight. And we could do unit conversions to find out exactly how much milligrams of this medicine the patient would need, but another way to do it is this thing called proportions. So what a proportion does is it pretty much says as the weight of the patient or mass of the patient in kilograms increases, the amount of medicine is also going to increase. So that's what's known as a direct proportion. The general setup of a proportion, direct version, would be A over B equals C over D. And this is the only time you can say the words cross multiply. So when you cross multiply a proportion, you get A times D, the top of one side times the bottom of the other side, is equal to B times C, the bottom of the left-hand side times the top of the right-hand side. Both of these are considered proportions. It's just the standard setup is a fraction equal to a fraction. This has nothing to do with a fraction times a fraction, so be careful of that. So the way you're going to set up your proportions is we're going to set it up according to this ratio. So when I say 5 in the top and 1 in the bottom, in unit conversions you have to put the measurements next to it. With direct proportions, you generally just want to get the order of them right and know which one's which. So the top number is going to be your milligrams. The bottom numbers we're going to deal with are going to be kilograms. So we want this to be equal to the number of milligrams the patient is going to get for being 250 pounds. Now, well, of course, there's a little problem. You can't have 250 pounds down here because the bottom number of this proportion is kilograms. So we still have to go through the 250 pounds. It's a unit measurement, so we'll just have that as over 1. And we want to get rid of the pounds, and we want to change it into kilograms. And from lots of discussions from before, it's 2.2 pounds for every single kilogram. So we need to just take 250 and divide it by 2.2. When you do that, we get 113.6. And of course the pounds are going to cancel, and all you're left with is kilograms. So this is 200, oh, I'm sorry. Undo that. 113.6 kilograms is the weight of the patient, or mass of the patient, now that it's in kilograms. So that's going to go here, 113.6. So the milligrams are going to go in the top, the kilograms, the patient's weights, are going to go in the bottom. What we don't know is this variable x. Now, you could cross-multiply to solve and set it up as AD times BC. But there's really no reason to do that because what you're trying to do is solve for x. So a shortcut would be to multiply both sides of the equation by 113.6, and the final answer will be 5 times 113.6. So let's see here. X is equal to times 5, 568.2. So this gets 568.2. Now, unlike the unit conversions, it keeps the measurements with each one of the values. Proportions will lose them for a little while, so you just have to kind of go back and say, what does x really represent in this problem? Well, x is in this location, and x is in the top, so it represents the milligrams of this medicine. Another type of proportion is the weird one, which is indirect. Now before, the direct proportion, as one got larger, so did the other measurement. An indirect or an inverse proportion, as one measurement gets larger, another one gets smaller. So for instance, one day you drove to work at 60 miles per hour and it took you 30 minutes. The next day you drove to work at 70 miles per hour. Now, if you go faster, the amount of time it takes you should go down. So that's what it means by indirect or inverse proportion. And here we would just want to know how much time do you save by actually driving 70 miles per hour compared to 60 miles per hour. Now the assumption is driving to work you're going to do the exact same path, so the distance you travel is exactly the same. The indirect formula is a little strange. It kind of looks like a proportion, but the positions of them is a little different. So for this one, it's how fast you're going, number one, the time it takes you, number one, is equal to how fast you were driving for the second part of the trip and how long you were driving for the second part of the trip. Now, when you go rate times time, that literally equals distance. So that's saying the distance on the left is the same as the distance on the right. And you get this nice indirect setup. Now, the main difference between indirect and direct is with direct you're setting up R1 over T1, R2 over T2, but those variables don't work as a direct. So the indirect would be to multiply them rather than to divide. So as this speed goes up, this time should have to go, as this speed goes up, this time should have to go down to keep the equality valid. All right, so let's plug in what we have. We have 60 miles per hour for rate 1, and time 1 becomes a little, you have to think about it for a second. One way of dealing with this is 30 minutes. This is miles per hour, and you were taught that if you have miles per hour here, this really should be hours. The cool thing with proportions is, to change this into hours, you would have to divide by 60. Indirect proportions, this is. So to change this one into hours, you would divide by 60. Over here, you'd be doing the exact same thing, dividing by 60. So technically what you can do is multiply both sides by 60s and work in minutes rather than in hours. So even though this is miles per hour and this is minutes, because of the way this is set up, it's going to work out rather nice. So rate 2 was 70 miles per hour, and T2 I have no clue, so we'll call it X. Now to solve this, all you have to do is divide by 70. And type in your calculator, 60 times 30 divided by 70. And you get 25.7. So you get X is equal to 25.7. Now again, because the measurements aren't being carried through the problem, you have to go back to the beginning. X represents T2. T2 is going to have the same measurement as T1, and T1 was measured in minutes. So this would be minutes. All right, but that doesn't answer the question. It says, how much time did you save? So you take your original 30 minutes, you subtract away your 25.7 minutes, and you get a grand total of 4.3 minutes. Now, because it's not 0.5, it's not 4.5 minutes, so it's a little less than 4.5 minutes. So by speeding 10 miles per hour faster to get to work, you save a whopping 4 minutes. Don't be late to work. Here's a problem that's very common in algebra and in chemistry. You have a solution that you have, and you have a solution that you need. And this is a simplistic version. You're not mixing two different concentrations together. What we're going to do is mix a concentration with water to dilute the concentration. So in other words, we're going to go from a 6 milligrams per liter concentration, and we want to drag it down to 4 milligrams per liter. And the easiest way to do that is just to add water. And then we can avoid a lot of the messy algebra that's involved in this problem. So the formula that we're going to use is a proportion formula based on concentrations, and it goes concentration of the first one times its volume is equal to the concentration of the second one times its volume. And again, it's an inverse relationship, because if you increase the volume on this side, then you have to decrease the concentration, because the product of these two For instance, milligrams per liter times liter leaves you with just how much of the pure stuff that you have. So again, these two sides have to be, stay equal to each other. So we know the concentration of the first one is 6 milligrams per liter. We do not know the volume of the first one, so I'm just going to put X. The second one's concentration is 4 milligrams per liter. And the volume of the second one we want to have is 5 gallons. Now again, C2 is measured in milligrams per liter, and here I'm putting in 5. So what happens here is, because the volumes here and here would be converted into liters exactly the same, I can cancel the conversions and work in gallons in this inverse or indirect proportion. So it's kind of a nice thing to have this proportion set up. All right, and then to solve for x, you just have to divide both sides by 6. So the answer would be 20 over 6, or approximately 3.33, forever and ever, but we'll just go 3.33. And this is measured in whatever x was. X is representing the volume, and our volume's original measurement was gallons. So this would be gallons. So what this is saying is 5 gallons of the 4 milligram solution has as much of the milligrams as 3.3 gallons of the 6 milligrams per liter solution. So the question basically says, how much of the 6 milligrams per liter solution, that would be this one, and how much water will you need to get to this new mixture? Well, I already have 3.33 gallons of my 6 milligrams per liter. I need 5 gallons. So the last step would be to take your 5, subtract the 3.33, and come up with the final answer of 1.67. And this is of water. So when you mix 1.67 gallons of water with the 3.33 gallons of the 6 milligrams per liter solution, you will end up with that solution, the 4 milligrams per liter.